doesn't necessarily have keyboard lights.
Right. I guess it wouldn't technically.
Yeah, so that can be an issue.
But yeah, in any case, the main thing was being a pain in the rear. I guess
Okay.
conditions don't want to install properly.
I don't think there's anything new on the website.
So I
or
have this
site.
tiny screen, and I just wasn't going to deal with that. And it's just, no,
I
can't.
wouldn't. You mean your virtual machine is a tiny screen?
Yes.
Yeah, I've
And-
heard those before. It's kind of annoying.
And the way to fix that is to install the guest editions. But mine was griping about not having the proper header files for the current running version of Current.
Ah, lovely.
So it would install like 2 or 3 parts of it, but not the part I wanted. The other nice part, not the part I needed to make it functional.
Yeah.
Yeah.
Yeah, that could be an issue.
I remember when you actually gave us that virtual machine for last semester for the buffer overflow project and security. I recall that I had to actually SSH onto it if I wanted a full screen that had nice, convenient command line interface, because otherwise it was a tiny little screen, and like if I got out of Vim, it would still keep the stuff like the output from the Vim program on top, and it was just annoying to use.
Yeah, you have to get the guest editions to install properly is what it comes down to. Then you can get the scaling mode and the seamless mode and the nice ones.
It's a
Yeah.
giant pain then.
Yeah, SSHing into it I
Normally,
thought was the easy way.
I've always had them just install like that without a hitch. This version of Ubuntu is just giving me the finger.
On an old laptop, I actually had a virtual machine installed for a desktop Linux. It was actually a graphical user interface. I never used the graphical part. I just opened up the terminal and played with that. So there's no point in having the graphical part anyway.
I've seen an Ubuntu version before where when it was installed on the computer, it would only use a little tiny bit of the screen. It was on an old laptop and it didn't have the right video driver for the obsolete card anymore. And so the previous version of Ubuntu would work fine in full resolution, which is like 1024/768, but after update it would only run in 640/480, which the LCD was scaling to be, just in the center.
Yeah, and
Which
that
is
was like
irritating,
the
too.
3rd or 4th problem I had when trying to install that virtual machine. Because I hadn't installed the VirtualBox on my machine yet, so I didn't know it had this little quirk as to where they've apparently hardened it on Windows. So if you have some modified Windows system files, it gives you the finger and says, no, you can't run me.
I see. But you probably have some. Yeah.
My
makes sense.
problem is that I have to where it modified so I can use custom themes on my Windows so it'll look nice. And apparently it checks one of those theme files. Because I only have 3 modified files on my machine, all of them based towards the theme.
Well, probably
That's
that's
it.
3 too many.
Apparently. So I had to look up and try and find the last version of VirtualBox that worked with mine, with those modifications.
Oh, I never tried running VirtualBox on Windows. Maybe it works better to host Linux instead of Linux. I don't know. There's no particular reason it should, though. The whole idea of the virtual machine is that it doesn't matter anymore.
Yeah, well, apparently Oracle got a stick up their rear and decided to make it so you can't use it when you have a modified system. Windows-wise, at least.
They're protecting you.
Does anyone have to take the HRPT 135 class next semester, like interpersonal communications? I'm actually not taking it because I'm taking real analysis instead, but I don't know. Why would I have to interpersonally communicate? That's weird.
Well, programmers do have to do that. I mean, that's like our one of the main complaints from industry. They say you make these programmers and their technical skills are great, but they can't communicate with anybody, so we can't tell them what we need them to do, and they can't tell us what the program does.
No.
Yeah, I think they want to make us do the public speaking now, so we can at least do presentations properly.
Yeah. So that's you got to learn how to interact with the non-technical populace.
I just bartend some weekends and call that interpersonal communication.
Yeah, that's
it's always
probably
really
fine.
awkward though, because I never know how to ask people what they want to drink. Like, what's the best way to ask them? Hey, what would you like? Oh, wait. Hey, what would you like?
Yeah, that's a pretty good way. Yeah.
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 It's always very awkward.
Or
Yeah.
what can I get for you?
Well, if you get tired of saying it, you can just put like a sign on your head that says that.
Well, half the time they look confused that I'm asking them that question, and they realize I'm a bartender.
Oh, I see.
I don't know if most men actually bartend. Oh well, I get good tips. I don't care.
If it makes you feel better, my uncle was a really damn good bartender for a long while.
Oh, we gotta go. over this,
Counterintuitive bit is that, well, he's not exactly a straight dude, but hey.
Oh well.
I just noticed a joke in the kernel.
Granted,
So we did discuss fork and kernel and things today. And apparently there's a problem with the POSIX compatibility on Linux as a version 0.11. I'm assuming it's a joke because POSIX compatibility is far from complete. But there may be some other joke embedded in there that I'm unaware of. Oh yeah, so fork and how fork works and where we left off actually. So we left off in main.c last time we were talking about this, and we write down here, and then I showed you all this how you use fork in a shell. But today we get to follow the fork rabbit hole the other way and see how it works in an operating system, which is going to be fun. And we get to talk about pause. And see, both of these things are things that can be talked about for quite a long time. So anyway, fork. It's called from right here, and it's actually a system call. I believe there's a mention of it somewhere further up here. There we go, where we say static inline syscall 0, and we actually make a place to call the system call fork. And I looked at that one before. But if we look in this kernel side of things, as far as where it goes, the system call is going to end up here, ultimately, at sysfork. There's a kind of a table of these things, and it's in include, and this one's going to be mentioned in unit.std.h, which is just standard Unix functions. And so there's the header for the fork function, although not the implementation we're using. Oh, anyway, so if we go back to where I was a minute ago, and take a look in here. So this is what the fork function does, and most of its things are taken care of in these two functions here. We'll talk about copy process first. It's kind of the main thing that goes on here. And these are both in a file that's very intuitively named fork.c. Okay, so this is fork.c, and this is copy process. So that's where we're going. Remember the fork, you have some kind of parent process, which is actually referred to as the father process in one spot. I've never seen this term for processes. Always parent. But anyway, it's called the father process here. So apparently processes are actually gendered. I did not know that. But there we go. Okay, and so anyway, this parent process forks off, and you have some kind of child process, which is a copy of the parent. So processes actually reproduce in an unusual manner here. Basically, there's just one parent, and a duplicate of them is created. So it's not really biologically inspired particularly. It just occurred to me that in certain... What's that?
Single-cell organisms.
Yeah, there you go. Single-cell organisms. Sounds good. Just occurred to me that actually in some languages, such as Spanish, everything is gendered. Like chairs are gendered, tables are gendered, etc. And so Linus was from a non-English speaking country. Maybe this just made sense in whatever language they speak, in the Netherlands or wherever it was. Finland, that's it, Finland. Anyway, I don't know if that's true or not, but usual terms parent. Okay, so copy process. And as parameters up there, we got a list of x86 registers. So this function is highly non-portable to other architectures. So we're going to go and make a task structure here. And we end up using a free page from memory. We'll talk about the memory manager a little later. And so what we basically want to do is have this task structure. And if we go look at a struct task struct, include, okay, I've got our task struct everywhere, if I can type correctly. Looks like it's in scheduler.h, which is where it should be, because that's where all the scheduler stuff is. So, these are hard-coded, don't touch. We can look, but we better not be changing them. And so we got states for the process, counter, priority, etc. Priority in Linux and Unix type systems in general is done by niceness, and a nicer process has lower priority. So it's just a model of the Unix came out of the corporate world. IBM wrote it, and apparently in the corporate world, if you're nice, you don't get any of your tasks done. And so niceness and productivity are like inversely proportional. And so that's how priority level goes. Priority is the inverse of niceness. Anyway, so there's a priority. And starting along, although usually it's from 0 to 20. This varies from one Unix to the next. I can have received a signal, and I can have a handler for that signal. In fact, there's 32 handlers we can have here. We'll talk about signals a little later today, too. Signals are fun. Okay, and under various fields, you have exit code. There's things about which user is running it, and a group and kind of stuff. How much time is this thing used? I don't know what useMap does. inode's down here. So it's got a working directory, some directory that for that process is considered open. And if you're writing a program, you can actually run cd inside the program and change the working directory. Well, changes here. And that's how your shell works, but you can do it in other programs too. And it's got a root directory, and it's got an executable. I'm assuming that's the program itself. We go run, and other stuff. You can have an array of files that are open, and so it actually tracks here which files does a particular process have open, because these are something it needs to know. If you have a file, and you have a file tree, and your file tree has a link in it to some file, and your process decides it wants to use that file, and then you go and delete the file, you basically just remove the connection to the file from the directory tree, and when the process finishes, the file will go away because there's nothing more connecting to it. And so unlike in a Windows system, you can actually delete all the files out from under a program and it won't care, unless it tries to open one later. Now, if you open a program and it's busy opening all its files and you're busy deleting them, you might end up meeting in the middle of some kind of problem. Anyway, so I got a file pointer there, description structure, etc. Okay, so that's what's included in a task. And there should be some kind of, I missed the whole struct here. There should be a struct that has a bunch of other stuff in it. And we'll see it from the other side. It'll be fun. Okay. Okay, so our task is we got to take this and copy everything over, and that includes some stuff that doesn't just naturally come over here. So this line right here, we copy to the process whatever our current process is. Just make like a deep copy, but it's only kind of a deep copy. It's not recursive in any way here, and so anything that's a pointer inside this struct, whatever it points to, is not getting duplicated here. And so he's got a note about that. After that, we set up some stuff here that's going to be actually different. There's not that many things that are actually different from the parent and the child, but we got a few of them. So the process ID is one that we have to have found for. We'll find last PID later. Going backwards there. Obviously, the parent is different, and priority level, I guess, is going to be the same. Well, the counter is the old priority level, apparently. Signal and alarm things are 0. The time count stuff is 0'd back out again. And a few other random things. Oh, but then we got this whole TSS structure inside here. And you can see it's full of CPU registers and that kind of thing. We look in here, TSS, right there. TSS for this stack. It's got a TSS struct. There's a TSS struct. And this is the state of the CPU. For an x86. And so it's got basically a list of registers here. And all the registers have to be backed up, because remember, when the scheduler is switching between processes, it has to switch what the registers are in order to revive everything in the correct place. It's kind of like my brother works at a security company in Texas, and they have desks there, but the desks are used by multiple people, and so when you go sit down at a desk in order to start working again, you might have a few things to do to set everything up right. For example, he carries his own keyboard around. He's just as much of a nut as I am. And
Can you blame him?
what's that?
Can you blame him?
Well, he said part of it is because he likes his keyboard. He has a fancy mechanical one, like a fancy one. It's like backlit and things, not an old IBM one. And because he works a real job instead of teaching classes. And it said his keyboard is less slimy than the other ones too, and he likes that.
He probably doesn't spill drinks on his keyboard either.
Yeah. But anyway, so with each worker, what they have is lockers, and the worker can put all their stuff in a locker instead of keeping them in the same little workspace. So when you switch, you got to take everything that was used for work and go store it somewhere. And then when you switch back to that worker, everything needs to come out of the locker and go back. So we're doing the same thing here. We got one processor. We got a bunch of different tasks that are sharing it, and so anything that has to be set up on that processor for the process to continue on needs to be saved, so we can get right back where we were going, where we were before. And so anyway, that's what this is doing. And then you notice we got i387 here. So this is kind of back from the days when you would have a separate i387 math coprocessor. We might or might not have anything to save from the floating point unit there. And if we don't, that's fine. We can just ignore it. Okay, so back in this one, fork.c, we're going through and putting all this stuff in here. And I don't understand the x86 architecture well enough to tell you straight off why you have to AND these with positive numbers here. ES is going to be a shorter register, a 16-bit register. And so my guess is we're doing some kind of conversion here because it probably got like a long 32-bit value for these. But why do they have to all be ones? Okay, so let's see. And then we have to do some copying some memory, because when we do it, when we do this kind of transition, when we take one process and duplicate it, we don't want the next process to, we don't want them to be right into the same bit of memory, because we don't want the two processes to end up causing problems with each other. When you take a shell and you spawn off a child in the shell, and then you use exec CVE or whatever to replace the child with a different running program, you don't want that program overwriting the memory from your shell, right? That'd be bad. So we have to duplicate the memory space. And since the child gets everything that the parent had in memory, that needs to be duplicated, maybe. And see, on a modern system, when you do this, you don't duplicate things until the child actually changes something that means that you have to have duplication. Because if the child just looks at stuff and the parent hasn't changed it, and the child doesn't try and change it, there's not really any reason to do any duplication yet. And so a modern system will hold off on the duplication until it needs to do it. I don't know as this one does. I was looking at that a little bit. So we got this copy mem up here, and copy mem is right up here. And we're going through here and making a new page table. So we set up a new base level for each of these. These are the things in the child. Where's the code segment, etc. And so then, I set new bases and things, and then we copy page tables over. And it kind of looked to me like we might actually be making a real copy here. Anyway, and you can have a memory error, no memory. Which also kind of speaks to duplicating the entire thing. Anyway, I didn't look into it that much, but I think we're duplicating it. That's fine, it'll work. Most of the stuff in Linux 0.11, it's not necessarily the best way, it's like a way that'll work. And I mean, if you ever do it, think about holding off on the duplication, but make it work first. Okay.
Well, with modern systems, it's not such a big deal unless you're doing something crazy.
Well, it isn't. I mean, if you have a movie player and you have a feature where the movie player will spawn off a second process that is a simple web server that will wait for instructions from your smartphone to tell it what to do, so that you start up your media player and then you start up this process that controls the media player, and then you just use your phone as your remote. Well, you don't want to duplicate the entire movie into the child.
As I said, unless you're doing something crazy.
Yeah. I suppose if you're in a situation where your operating system was doing that, you'd want to use some mechanism other than making a new process. Like Java, for example, has threads inside the virtual machine, and that'll get you past any kind of weird operating system limit like that. Yeah. Incidentally, if nobody's done that yet, a smartphone, like a remote app for controlling movies, they should. Because seriously, everybody's always lost the remote under the couch, right? I mean,
I thought some phones did have a remote app.
they probably did. Somebody's got to have thought of it.
Yeah. I just believe the only stipulation that I've normally seen is that everything has to be connected to the Wi-Fi.
That would make kind of sense and kind of not sense.
Well, but they have to have a connection somehow, and depends on if they would use and phones don't always have the same infrared capabilities that a remote would have.
It's probably more a deal with your firewall. Because the phone, if it's connected to the cellular network, it can get out on the internet. And if it can get to the internet, it can get to your house. But if it can't get through your firewall to your computer, then it can't
Well, I was
get a
talking about a
message
smart
through.
TV or the computer.
Yeah, well, same
You
thing.
have
It
to
can't
have
get
it-
through
you
the
have to have a
firewall.
route somehow, and
Yeah.
probably local would be the best. But
Well, same thing. I mean, smart TV is a computer with a TV screen. And yeah, I mean, it can't get through your router necessarily. But it would be really handy. They probably have this, but they should really have like ways to leave a phone somewhere and carry the matching one, and then you can like listen and use it as an intercom or whatever. Oh, anyway. Should have a trail camera, like for deer hunting app for it. And people, everybody go leave their phone in the woods and get rained on and use somewhere.
that's where you get a waterproof case, though.
Yeah, I guess. Okay, so we're doing some duplication here, and that's fine and not fine. Yeah, going through. Oh yeah. So after we've dealt with the memory and that kind of stuff, we're gonna have to copy the whole file array. This is pretty straightforward. It's just a loop that goes and copies stuff. In our open is the number of files we have open on this process, and so we're just going to go ahead and copy them over. So the child has all the files open that the parent had open. And this does have certain implications if you're making this. I mean, if you got some parent that's got a bunch of files open, and you make a child, and then you get rid of the parent, and the child never uses any of those files for anything, they're still open, unless you close them in a child. So it's just another thing to keep in mind. If the child stops running, then all its files get closed, and that's fine. In the beginning programming classes, a lot of times we kind of beat into students that you really need to close files that you've opened. And so you end up with this program where the program is 20 lines long and the last line closes the file. On Linux at least, that is quite unnecessary because the operating system will close the file when your program's gone. Same as you don't really need to free memory that you've mallocked right before you end the program because the program's going away anyway. And so, I mean, this is like cleaning up your house before you burn it down, you know? It's going to happen. Anyway, the child does have these open, and so if you have a long-running child, that is something to consider. And when you make a daemon, background process, you usually have a parent process, and then you fork it to make a child, and then you kill the parent. And so then the child continues on without being connected to a terminal or anything that the parent started from. So once it's daemonized, it keeps all of the files open that the parent had open. So if the parent had to go open a whole bunch of configuration files to decide how to start the child, then the child's still got them open even if it doesn't need them anymore. Okay, but you can just call close and fix it. Okay, so that thing's all copied over. The current print working directory, the I count right here. So you notice the PWD there, current arrow PWD. When we were in this before, back. Okay. That was in schedule.h, and that was up here somewhere, PWD, there it is. Okay, so that's a struct m_inode, which is probably not defined in schedule.c. Okay, it looks like it's in fs.h. I don't know why it's M underscore inode. Oh, anyway, so here we have our structure, and for an inode. And I'm assuming this is the same thing as an, oh, we had two different types of inodes. We had three different types of inodes. We had D inodes, M inodes, and I thought I saw P inodes. Okay, so Linux 0.11 has more than one type of inode. I don't think that modern Linux has more than one type of inode. And NetBSD doesn't have more than one type of inode. So this is a little unusual. But anyway, you got these different properties describing your file here. And one of them is going to be the number of links to the file right there, and links. When those all are gone, the file can be safely disposed of. And if I remember right, that's what we were changing a moment ago over here. And fork.c, oh, I count. Okay. I count, which is probably a use count right there. How many users do we have? Here's just an unsigned short, that's 16 bits, so you can't have more than 65,000 users of a file at the same time. There's a lot of silly limits like that in Linux 0.11 that go away later. Okay, where were we? We're in fork.c. Okay, and I say silly limit because there's not that much reason for it, really. You know, it's just a matter of how big these structures are. In Linux 0.11, you can't run 65,000 processes either. And so there's no way that this could be a problem. And so you might as well use 16 bits there, but why can't it run more than 65,000 processes? It's just, you know, decisions on the sizes of these types. And I think this is kind of more of a proof of concept operating system really than anything else. Low number is fine, and in fact, I very rarely run 65,000 programs at once on my computer. But, you know, it's the kind of limit where, you know, why? What if you have some kind of situation where you really did want that, other than a fork bomb? And there is a limit on any system, and a fork bomb will find the limit.
Sounds like a fork bomb is a nice, safe way of finding that limit.
It is, yeah, yeah. You got to do it on like not a software computer, but yeah.
Why?
Well, because
sometimes you walk down and then hit the button.
You don't need root access to set off a fork bomb. The administrator can potentially thwart your fork bomb by placing a limit on the number of processes per user that's lower than the number that's allowed in the system. Say limit everybody to 2,000 each, and you know, you can have say a 32-bit number, 4 billion on the system. Well, then if you set off the fork bomb, it's only 2,000 processes, and it'll make everything run slow, but that's it. The normal configuration, and the way our software is configured, each user can start as many processes as they like until the system just doesn't have any more space. So if a regular user starts a fork bomb, then once the fork bomb has populated the entire process table, then nobody can start a process, administrator or not, because there's no more space in the process table.
So was that software configured so I couldn't do anything bad with a fork bomb?
You could definitely do something bad with a fork bomb.
So
That's
if
why
I
he
run a
says
fork
no
bomb on a
fork bomb.
soft drive, I get in trouble then.
I shouldn't do that. Yeah, that would be bad.
Yeah,
Depending
that's
on
a smart
the
idea.
particulars, I might end up having to walk down to the data center on that one.
Okay, I'll avoid starting one.
Yeah.
Yeah,
'Cause you
that's
can't
what I was
SS
saying, please don't, because you have to walk.
You can't SSH into it without starting a
Yeah.
process.
That's pretty bad.
And you can't exactly start a shutdown process if there's no processes, right?
Well, yeah,
Or is
yeah.
that the exception?
So if you have, say the fork bomb goes off on your machine, and you've got 3 terminals open, a common thing for people to do, you can exec stuff in your terminal. It uses the terminal's entry in the process table, so this is a one-time deal. You run it and you're done with that terminal. But you use one to figure out the name of the fork bomb. The next one, you run kill all, but you can't try to kill the fork bomb at this point. If you do, you got 1 kill all. The fork bomb has like 65,000 bomblets making more processes, and 65,000 is going to beat 1. So you have to run kill all and stop the fork bomb processes, but leave them in the process table. And in third terminal, kill them.
That sounds tedious.
Although actually, on the third terminal, you may actually be able to run processes normally, because when the second terminal went away, you ran kill all and you stopped all of them, and then kill all finished, leaving exactly one spot left in the process table. And so you may be able to make a child on that third terminal and use it as many times as you want. But if you make any mistake, you're done for with that 3 terminals. And if you got like 10 terminals, then you got 7 mistakes to make.
I have to admit, the fork bomb project sounds like a lot of fun.
Yeah, but see, you can prevent this series easily when you're writing a fork bomb. Just make sure each bomb has a randomized name.
Yeah. That would work.
And then they're totally done once it's off.
Oh yeah, pretty much. So yeah, that's how the process table works. Print working directory. Oh, and you'd have a whole bunch of uses of a file with a fork bomb. What somebody would have to do is come up with some sort of better way to run the kill process. I mean, you could write a program that goes and kills everything that was started within the past 2 minutes. I mean, that might be fine. Or kills everything that was run by the user that's running the fork bomb or whatever. But you'd have to burn terminals figuring out what to do exactly. Oh yeah, so this whole set all that stuff up and off we go. It's called last PID. Well, yeah, it's called last PID. Okay, so everything's more or less duplicated here, and finally set our state to task running. Mentions do this last just in case. Yeah, I suppose, kind of. I mean, if we're running this code here, and then the scheduler got called and decided to start it running, even though he hadn't finished populating the structure, we'd be in for a problem. The actual likelihood of that seems quite small, considering this is this is code in the kernel. It's going to be run in kernel mode. I don't know if the kernel was preemptible back in those days. It is now, and so if it's not even preemptible, then there's not really any way. But it probably
Good
makes
practice.
Linus, makes Linus feel funny if it's possible to start it when it's not done. It would make me feel funny to leave it that way. And you also don't want to leave problems in here for if the kernel does become preemptible, which eventually it did. These days the kernel is interruptible in about anywhere except an interrupt handler. So it's all find empty processes. If we go back to the interrupt over there, and the interrupt was in syscall. Was it in that? It was in a .s file. System call is .s. Yeah, right there. Okay. So we call find empty process first, and then later we call copy process, and we do some assembly stuff in there. CS250 stuff. I have so many great examples if I ever teach 250 again. So the find empty processes here. It's not a very long function, and it's actually not very complicated what it does. It finds us a spot in the task array. It's just an array of tasks that the scheduler can pick from. And it finds us a process ID. And once we have both of those, then we're done. Okay. This whole thing right here, though, this is kind of an interesting piece of code. It uses a goto. See, we got goto repeat right here. Repeat goes up here. So this is kind of a looping construct there with that goto. And here we're incrementing the last PID. And if we go too far on the last PID, then we set it to 1. I say too far because if we look up here at last PID is a type long right here. So look at that and be like, well, okay, so why is it a long and not an int? And if we look at this, sizes that see, it varies based on which machine you're on exactly. Okay, %sign D, oh yeah, we'll go long, %sign D, int, %sign D, new line, size of long, size of int. Okay, see how big they are in this machine. It's going to gripe at me because I didn't put a return on there. We got the wrong type, but it's probably fine. Okay, so on this machine, a long is 8 bytes and an integer is 4 bytes. So we're looking at a 64-bit value on here. But when Linus wrote this, it was going to be a 32-bit value. When we switched to the AMD 64 or x86 64 architecture, the definition of long changed and integer didn't. And prior to when Linus was writing this, there were a lot of machines around in the 80s where an integer was 2 bytes and a long was 4 bytes. And so at certain times and on certain machines, long is longer, but this is not actually quite universal, and sometimes it's the same as an integer. Anyway, so the choice here, using a long for this, does give the bigger of those two data types, and so that's available for process IDs. And it's probably not a constraint here that we can only open a file 65,000 times, because our process IDs, I can go higher than that if they need to, not a problem. Look at this also, you might say, well, isn't this exactly the sort of thing that the signed size t, S size t, was designed to solve? And yeah, but they hadn't done it yet, the whole size t. And if you go here and you say grep, say in recursive for size t, everywhere in here, you find nothing. Size t came about later than this. So anyway, lacking a size t, Linus uses a long.
Which is the next best thing when you don't know what you get.
Yeah, right. The thing about the size t is it's guaranteed to be the same as the address length on whatever architecture you're on. Long doesn't have any guarantee like that, actually. In fact, integer doesn't have any guarantee on size either. So you got the size thing there. Okay, so the logic in this thing, maybe if you look at this, we're going to increment our PID here, and then we're going to go check and see if that PID is used. And if it happens that it is used, we're going to go back up here and we're going to pick another one and then check to see if it's used. It's not that complicated of logic, really, but it's got a goto in here. And so I had to think about it, like what would you do if you didn't use a goto? I won't save this chain. Obviously, because it's not even running on here. Okay, so if we want to non-de-goto this, we can do something like while, continue. Well, we have to do something here in terms of condition, because that's where while wants this kind of thing. So
well, the condition on the if on bottom of go that was the go-to should work, but you'd have to.
Yeah, you can do that. You put it like this here, up there, and would increment it, but you're going to have to do that in the loop too, which I guess you're going to do later now. And then, well, you can't do that later. Maybe just go ahead and do it there, and then take that one. I did that wrong because I pushed the wrong button. And then instead of that, okay, that works, I think. Okay, now we have to run through this whole thing though. So it doesn't really work because we're not repeating that task, that one down here. So that's not in any way equivalent.
I didn't know about that command. There's a lot of nice commands on Vim I don't know about.
Which one? Undo?
Yeah, I didn't use that one.
Yeah, there's probably a shorter way to do it too. So that doesn't really take care of it either. So you guys start looking at it, and it's like, well, wait a minute, how would you do this stupid thing? And so one way out of this, you could say repeat equals 1, and down here repeat, and so then down here, you'd say we're not going to repeat it. Okay, and then down here, then we want to change repeat, and we're going to actually need 2 lines for this. And break, which is going to break us out of the for loop, so we don't need to continue going down it. And so that'll pop us back up here and continue to run down there. So I think that has the same logic. It's kind of longish, and I actually think his way is clearer. But that was interesting use of goto. It can be argued for. There's people that would say to just do the top one because goto is bad. And there's also people that might say, well, the solution here is a nested function. GCC didn't support nested functions in 1991. It wasn't until, I think, 99 that that feature came in. So that wasn't really an option here. Okay, so I closed it, did not say to change. Okay, so that's what that thing does. Finds this last PID and that kind of stuff. Okay, where am I going in life? Go to loop, does it make sense? Yeah, went long, went outside C, went unsigned. I don't know. I never did quite figure out a good explanation for that. So there we go. Oh yeah, so after that we go back and we use pause. And so pause, talking about the pause right down at the bottom of this thing. And that would be right down here. So this is process 0 here. Remember we moved to user mode, running in priority level 3 at this point. And so coming down here, this is what task 0 continues to do. It just, if anything happens, it, if it ever gets scheduled, then it pauses, calls pause. And so pause, instead of system call, it's going to be up, wherever these are, yeah, right here. Syscall 0 sets that up. And so we should be looking for like a sys pause. And so if we, we can look for the syscall table here probably. System call. I find it. I would thought it would be in there. Found it this morning easily enough. It appears to be in schedule.c. I'll just skip to there. Yeah, we've gone through enough system calls, you know the drill. That's the schedule initializer. Okay, so it doesn't do very much. What pause does is it sets the current task as interruptible and calls the scheduler. And so then the scheduler can go schedule something new. So really, this is it's kind of more on the scheduler here. Okay, so schedule is the scheduler function. The good code scheduler. We talked about that briefly last time. And so that's what's getting called here. Basically we're looking for, well, we got kind of two different priority levels here. Processes that have a signal get to go first, and so they can handle their signal. And then after that we have the scheduler proper. Okay, let's kind of interlude here for a moment and talk about schedulers, or signals. Signals, yeah, signals, that's where I'm supposed to be. Okay, so, FCS, okay, M handle signal.c. Okay, so I want to make a program that handles a signal. So if you have some kind of program and it doesn't stop, then normally you can kill it by sending in a signal, right? So let's make a program that doesn't stop. Okay. Sleep 1, print out, still going. Okay. Should be happy there. Okay, so it just keeps printing this stuff out. When we hit Control-C, it is done. Okay. So there's a number of signals here. Section 7 has a signal man page that lists them. And we've got one of them up there, signal number 2 there is SIGINT, or interrupt from keyboard. And so if we have an interrupt from keyboard, well, we stop the program. So let's go ahead and try and handle that. Look for SIG action. There's a SIG action function. You can see it in our manual section 2 here, a Linux Programmer's Manual. And so SIG action here, let's specify a signal number, a SIG action struct, and an old SIG action struct, which is going to be what the previous signal handler was. And so if we look down here, it's got a explanation of what a signal handler, a SIG action struct looks like. SIG action has a handler here. This is a function pointer,
And we've got a sig action function here if we want it, and a couple of other things. We have to populate the SA handler field of this thing, but I think if we leave the rest of this alone, we'll be fine. It actually mentions the SA restore element is obsolete and should not be used. POSIX does not specify it. So yeah, we'll just do the top one up here, the SA handler, and that should be fine. Okay, so this function is called sig action, and the struct is called sig action, which I always thought was confusing. Okay, so handle signal here. So we're going to call sig action, and we want to give it a 2 because that's the signal we want to handle. Keyboard interrupt. We want to give it a pointer to our sig action struct. So we're going to make a struct sig action. We'll call it a handler. It's kind of a generic name. That's okay though. Okay, so the address of handler. I think it wants a pointer, if I remember right. Yeah, pointer. Okay, and the last one I believe can be 0. The last one, you can make another signal action, sig action here, and send it a pointer to it, and it'll populate it with whatever the current handler is for that signal. But if you don't care what the current handler is, you just want to install your own, this will be fine. Okay, but we have to handle handler and that thing up there, SA underscore handler. Okay, so handler, actually dot, SA equals, so we're going to need a function up here. And this function should return void, if I remember right. And is that right? You can check. It has the function prototype right here. Yep, returns void, takes an integer. Okay, void, don't stop. Int param. What is a param? Let's see. Okay, I think it's actually the number, the signal. Okay. Okay. So then we just set this as our handler here.
You might want to put something in the printf function to put in %d.
Oh yeah, good point. Otherwise we'll get a segmentation fault. We didn't handle that signal. We can, but we didn't. Okay, storage size of struct sig action.
Oh, did you include signal.h?
Probably not.
That was a very confusing error when I first started doing some C programming. I thought, oh, why is this?
Okay, so it's going. I'm going to hit Control C. It stopped. That's very disappointing. So what happened here? We installed our handler. The handler is for 2, and did we get a different signal that we didn't expect? Did I hit band 7 signal? I don't think I did. Maybe I did. Because it should have the list down here. Sig int. Let's actually put sig int there. It's not that I don't trust this table, I'm just surprised it didn't work. That should probably just be 2. I still stopped it. Okay. I wonder if we're actually getting a different signal in that case. Because that, well, let's look at that table again. Okay. So I thought signal 2 interrupt from keyboard looked like what we were getting. We've also got, though, a quit from keyboard, sig quit. We've got a sig kill, that's number 9. And those are all the ones I see that are kind of killing like. Sig kill can't be caught, blocked, or ignored, so it's not that one. And we know 9 is kind of special there. Sig quit there, quit from keyboard.
So sig
Right.
seg, so you can actually handle that and just have it ignore when segmentation faults happen?
Yeah, yeah.
Oh, that's a great way to, something I'd like to do. Just ignore segmentation faults and keep running.
Yeah.
You didn't
That's
compile.
good. What's that?
You didn't compile.
Oh. I'm still dying. Let's cheat.
Maybe sig kill?
Sig kill. Sig kill was number 9. You can catch that one. Last time I did sig int and all the rest of them, and I called my sig action s, which was fine, and that was indeed the signal, and it worked. I'm not sure I see the difference. Oh, wait a minute. Did I put my loop first? Yes. I put my int in a loop before registering the signal handler. Okay, let's try that. So, it is harder to stop now. And I can push Control C and stop it so that it's running in the background. And then I can do PS, and I can see that it's A.out there, and I can say kill all A.out. And if I look at PS again, it's actually still there. But if I bring it into the foreground, it goes away. And so it's actually gone. Well, we had all of these signals here, and so you can see where this is going. We'll just go ahead and handle, what was that? Sig quit maybe? I don't know. And sig stop. I mean, that stopped it. That's not very nice either. So, duplication time. Okay.
So how are we going to stop the program once it does this?
Maybe kill all -9. So we can't do a sig kill there. That's not going to work. I'll run there, but okay. Control C, Control Z. Oh, it actually stopped it. Did I do that wrong? Thought it was or is it one of those ones that can't be caught? Ah, sig stop can't be caught. Ah, that's too bad. Okay, well, we're going to be able to do that one then. So here it is with PS. And we kill it, and we foreground it, and it goes away. There's one that's like a sig, the one that the kill all normally sends. It normally sends like a sig term. Okay, that's going to handle that too.
Could have just modified that one.
Yeah, you're right, it could. This doesn't work anyway. Okay, there we go. I'm going to open up a terminal over here. Yeah, we have block kill all, at least, well, that way. We can send it at -9, and that will do it in. But in general, we can handle those things. So that's why your terminal up here, you can do Control C, and my shell doesn't go away. And in fact, when you run other things, let's run Python, Control C, it says keyboard interrupt. It doesn't actually stop this. And so that's how they do that trick. Control D, end of file, will stop Python. And that's kind of a convention there.
I think Control D stops the terminal too.
Yeah, it does. It just means end of file. And so it's kind of an accepted convention that this is the end of your input to that program.
Okay, that works.
Yeah. As opposed to an attempt to rudely interrupt it. You're like, and I have no more to say.
Yeah. So what happens if you hit Control Z while on the terminal? I don't think actually, you might have done that before. I don't think it does anything.
Yeah, it doesn't do anything. But if you're running Python. Hey, you can stop Python. Now it's in the background. Yeah. So that's the signal mechanism. And yeah, signals are good. And yes, you can handle all sorts of stuff with those if you want to. It's kind of like exception handling in a way, because suppose down here in this list you decide that you want to handle sig-segv. Well, that means that for your program, you just end up with a handler that takes care of it if you have an invalid memory reference. And so then instead of crashing, your program can go try and deal with it. You can see how you could get to exception handling here if you really wanted to. Because if you take your entire program and you say, well, okay, we're going to kind of keep track of where we are in the program, and so then when we get an exception here, a signal 6 SegB, we'll go somewhere else and we'll maybe log the error, and then we'll get going again at some point where we can continue on. And so this is, exception handling predates C++, the whole idea here. It's been around in Signals, and I wouldn't be surprised if C++ used Signals somewhere in the exception handler. Oh yeah, so that's Signals and that kind of stuff. Signals are good. Okay. There's a floating point exception right here. I think this might pick off and divide by 0. Okay, so that's that, pop D, and we're back. The signals, we did sig action. Oh yeah, so schedule, and in terms of what schedule does, kind of starting to wrap up here. Okay, so the schedule.c, yeah. Okay, so over here, we'll check and see if there's any tasks that have a signal. And so we're checking to see if whatever our pointer is to our current task has a signal. And it looks like we work backwards through the list here. They say that because we seem to start at last task and minus P until we get to the first task. See if there's an alarm or a signal. So then with the actual scheduler, what we want to do is again just run through all the tasks. So I is the number of tasks here. And we're again going backwards. I'm not sure why we like going backwards so much here. It seems like either way would be fine, but we're going backwards. And so if there's no more to look at, that is, if this is 0, then we're, well, why do we continue on? I would have expected to see a break here. Oh, well, I was going to finish up soon anyway. Okay, this is if there's actually, I was actually wrong about that. This is if that entry is 0. So if there's no pointer in this array to a scheduled task, then we're going to skip it. Because if the dereferencing of P here doesn't have anything, then yeah. Okay, and assuming that there is something there, an actual non-zero number, we're going to look at its state to see if it's running, and look at its counter here. So running in here, I mean, obviously task running does not mean that the CPU is presently engaged in carrying out instructions on this task. Because if it did, we wouldn't be running this line of code, right? So this means that the task thinks it's running, I guess. It's been running through time slices, and it's plugging along like it's running and has exclusive access to the CPU, even though we're busy deciding if it should get to run or not right here. So that's what it means here. And so then we check to see the program counter here. This program counter is greater than C. C up there is -1. So we're going to try and figure out one that hasn't had very much time, I think is what this amounts to. So see, we keep changing C there. And we check to see if C is well, okay, the C is if our counter is greater than C, and if it is, we're updating C, and we're setting the next one to I. Okay, so moving along here, down there we're saying if C break. So that's going to be if C is positive, like we found one that's actually been run before, and we're going to run it again. And then down there we say for P is last task, and you're going from one to the other here. And looking at the counter plus the priority. Okay, so the counter here is more or less telling us where we are in the program. And so we're kind of basing this on how long a program has had before, and of course weighting it down there with the priority level to make our pick. And so once we've figured that out, then off we go. Switch to the next one. Really simple scheduler, really. the good code scheduler. It's not the current one, but it was there. Okay. I would have thought this would be in the kernel functions right here. Anyway, that's fine. So that's what the scheduler does. I want to go back over here and cover what init does, and then call it good for today. Cover what init does in a general manner. We'll cover it in a more specific manner later. Okay. So right up here, we did that fork right there, and we called init. And so init is right down here. And so this one, the book talks about init a lot and calls it process 1. Well, the first process there gets to be process 0. And so the process ID of this is going to be 1. I don't know if the number is like super significant, but that's what it's talking about when process 1 all the time in the book. So we go up there and call setup first thing. And so there's kind of two things that happen here. Setup is actually the bigger one, even though it's mostly somewhere else. Setup sets up our hard drive file system. And this is the first time we will have had a file system here. Remember, we started out with the kernel on our floppy disk and the bootloader. And so the bootloader was responsible for copying it's copying the head of the kernel, which copied the rest of the kernel. And so we got the kernel into memory. And we've just been rolling along on that so far without access to any of the file system that might be on the hard drive. And so that's what this part up here does. And presumably we could have a floppy drive file system that was mounted at this point instead if we wanted, but this seems to be set up for hard drives. And this actually was a time in computer history when you would put in your floppy to boot up the computer even though you had a hard drive. It didn't last that long, but there was a period of that. Okay, so, yeah, history. Okay, so I'll go set up the hard drive up here. We'll talk about that one later, because that one opens up a big can of worms. But after it's done, then we can go ahead and open stuff. The dev file system is created here, and there's other stuff created here. We're execing bin sh, so we're expecting to see a shell. We're looking at /etc, so we're expecting system configuration files to be there. And so this is where we're actually looking at the file system. And this kind of blurs the lines of what's in the kernel and what's not. I mean, this piece of code here, this is running at priority level 3 on the Intel processor scale here. And so that's the user priority level. And it's busy executing programs that are located in user space. And so it's not in the kernel directory here, it's in the init directory. So it's kind of arguably not even in the kernel. But anyway, it is here. And so the setup there is making a bunch of stuff happen in the kernel. But you notice for a while we've been operating in this user space mode. Like with pause up here. We don't just write pause, we go ahead and use the pause system call. So we're already treating the kernel like it's a library up here. And so down here, yeah, it's not really even in the kernel anymore. Okay, so this, we go ahead and open some stuff here. You notice we're actually forking again right here. And we're looking in etc and rc. And we end up making a terminal at some point possibly. But that might not happen depending. Well, I mean, fork could fail, that's unlikely. If opening that fails, then we exit. And if both of those are fine, then we go ahead and exec bin sh and actually start running a shell with these parameters right here. Remember, this is the same thing, exec cde. Better than CDP we used before. This exec family of functions, this is the same thing we used in the shell when we looked through that. And we're doing the same thing. We're forking and then execing, well, shell in this case. Okay, and then down here we're actually doing something kind of similar again in a loop. We'll get there. I want to talk about I want to talk about etc. So we're opening this etc rc directory. Well, if you look at /etc, it's configuration files. And there's a number of different initialization systems. So we're going over init here. And our last time we mentioned there's Upstart and systemd. Systemd is what iSoftware is actually using. And most of them work in similar ways. The ls grep -irc. We're going to get up with all these RC stuff, RC.1, 2, 3, 4, 5, 6, etc. It occurs to me now as a dreadful oversight that I've been a like exclusive Linux user for about 12 years, and I don't know what RC stands for. Anyway, so I got these different RC run levels. And maybe the R stands for run level. A run level is a certain level of functionality on the system. We got run levels defined here, 0 through 6, and RCS is going to be a shutdown run level. It's where everything goes away. Notice some other stuff popped up here with RC too. In general, RC is like an initialization kind of thing, like the way you set something up, and so whether it's the system or otherwise. Okay, here's rc.local. rc.local is a script that you get to add if you want in order to do extra things when the computer's turned on. As mentioned, by default, it does nothing. Here it is on Nimrod. And you can see I've got exactly one thing in here. ISO connect, this reestablishes my connection to iSoftware. And so that's handy. The other thing is, since I updated Debian, my ISO connect program doesn't work anymore. And even if I run interactively. And I haven't figured out why, or I haven't thought about why. But anyway, okay, so that's where RC stuff goes for. But anyway, in general, in this etc, if you go like rc.6, rc6.d, okay, we've got a directory here of scripts, and these are all different services that are available on the machine. Whether or not they're started or not, that's a different question. They're available. And if we were to type in here like service status all, we're going to see some services are running and some of them aren't. SMBD is running. So apparently I'm actually running a Samba server on here. It's just accessible from outside. So I need to make some changes in my configuration here. But anyway, SMB and Samba is a Windows file sharing service. I have it on here because I have to access some Windows file shares. Oh yeah, anyway, all this stuff. So either starts or doesn't start. And these run levels here, rc.whatever, they give you directories in order to put stuff if it's being run or not run. Okay, so that's the RC system. And the RC system on Linux 0.11 is probably different. Oh, there, it's fine. Okay, but that's what it's looking for in etc RC. And it seems to think that it's going to find something here in RC, and then when it runs the shell here, it's going to give it argv_rc and environment_rc, that's shell variables and things, which are up here. And so the environment here is setting home to /. The argv here, we're actually not really giving it any arguments. I'm not sure why this might set up the system, and I rather suspect that it's actually kind of a manual setting up of the system. RC here, we're not doing any like pipe duplication or anything. What I would expect to see here, that I don't, is somewhere where we take a script from etc RC and then feed it into bin sh by putting it either into this argv or running it into a pipe, like opening it up and doing some file descriptor duplication in order to run everything into this bin sh here. But I don't see that. It might be that there's some clever trickery involving this duplication right up here, where we're doing something with file descriptors. Maybe this ends up setting this to file descriptor 1 in a clever manner. I'm not sure. But my leading candidate is that it starts a shell, and then the user gets to do the run levels themselves. That's my leading thought here. I wish I had it installed so I could boot it up and see. Maybe the book says somewhere. I skimmed the book, but I didn't read it in detail on this stuff. Sometimes the source code that Linus did is really well documenting. I pick up the book when I don't understand something. I should have on this.
I like Linus's comments.
Oh yeah,
I think me and Linus, we get along fairly well.
possibly.
Although actually I've heard Linus is kind of, let's call rude would be a nice way of putting it sometimes.
He has that reputation, yeah. There's a number of kernel developers that have left over interpersonal communication issues.
Yeah, he got into some sort of controversy over the summer. I don't remember what it was. Or back in spring, I can't remember what it was though. It was something.
Yeah, and somebody left. It's happened a bunch of times.
Yeah.
Yeah, he should have probably taken an interpersonal relations class.
So that's the point of that class.
Yeah.
So you don't come off so blunt that people are like, you're a jackass.
Does every college student have to take it, or just the CS students?
Uh,
I imagine it's
I don't know.
probably just a bunch of the STEM students.
Part of the reason I don't know is you got here before me, and there's been all kinds of catalog changes, and so I have no idea what you actually have to do to graduate.
Yeah. I remember that class ever being on my catalog.
Yeah, we changed everything, and actually you can update catalog years, but you probably don't want to because you're so far along.
She
But
actually did update me to the 2013-14 or to a different catalog just because the previous one had 2 classes that were the exact same or something on it, so.
oh, okay.
I think
Yeah.
I changed the 2013-14 catalog.
With the 15-16 catalog looks a lot different. The entire general education core has been done differently. CS 108 is now a scientific ways of knowing, and so it actually counts as a science here. 108 being the new 110, and now it includes Java. So if you didn't know it was Alice, it's like totally different now.
Yeah.
And so then, and that's why it's like a
Yeah,
core class.
it's going to start counting as a lab of science as well.
Yeah, it's actually a lab science
Yeah.
course now. And so I don't know where interpersonal communications factors in here. There's a new diversity requirement.
Right up at the top.
Is it?
First section.
Written
So you have to
communication.
select speech.
Oh, so you select one of the following. So you can have speech, interpersonal, small group communication, or public speaking.
One I have to take is HRPT 130, whatever. I don't have to take it next semester, though. I'm taking real analysis instead.
Oh, okay.
If I
That sounds
remember
like
correctly,
fun.
the HRTP wasn't a requirement, it was an option of a requirement. Between that and something else, I thought.
HRPT.
Here's the main funny thing on this. So, I we got AI class this semester. I took 475 out of here, and it's available as an elective, but that means, 440 or 450 or any of these other catalogs, classes that are rarely taught can be put into degrees quite easily without hanging people up because they don't have a particular course. Because that's the reason that they're never taught, because when we articulate the particular courses here, like 475, then there's no flexibility on that, and you have to take 475. So we end up with scheduling pickles where like, this person has to take 475, so unless we want to just tell them they can't graduate, it has to be offered this particular semester, so no AI, no 450, whatever. And so this one it makes that all flexible. But yeah, you're also established, no reason to care probably. But, you can at least grumble about, kids these days. They get to just take whatever they like. When I studied at Lewis Clark, there wasn't even snow removal. Anyway, I'm out of time and I'm done.